The holomorphic condition of the superpotential gives a very strong conditions to determine the supersymmetric Lagrangian. First of all, I will review what was holomorphy. All the coupling and the superfuse does not have the dependence on the conjugate. So that this constrains the quantum correction strongly. For example, there is a non-renormalization theorem for the holomorphic superpotential. There is no additional loop correction beyond the tree level. And also we cover the physical coupling for the holomorphic superpotentials learn only through the wave function renormalization. For example, if we consider gauge kinetic term with the superpotential, we can define the complex holomorphic coupling with the gauge coupling part and the topological term theta. Then this holomorphic coupling runs only at the one loop by considering the gauge theoretic quantity, and only the superfield normalizations that gives the factor of the jet, which gives anomalous dimension. So that we can determine the exact beta function, so-called NSVZ function, for the learning coupling. So, based on this fact, we'll apply the holomorphic constraint to the specific model, for example, the supersymmetric QCD, or briefly the SQCD. The SQCD is defined with the gauge group of the SU, NC, the number of the color, then the method fields in the supersymmetry QCD the transforms under the SU of the NC for the Cork field and its conjugate. And the physical operators which will consist of supersymmetric Lagrangians must be gauge invariant. So the elementary superfields like the Qs are not observable. Also, over the gauge symmetry, we can also impose the global symmetry over this SQCD theory. For example, the Blaiber symmetry with the number of the Blaibers denoting as NF. And then there is a left-handed and right-handed Blaiber symmetry, like just the non-SUSY QCD. So the method fields the transforms with the left-handed one, but its conjugate so transforms with the right-handed one. And also we can add the additional global symmetry, which is called the U1B, for the baryon number. The method fields assign the baryon number of the +1, and the anti-matrix field assigned with the -1 of the baryon number. Then the Mason's type, which is consisted by the quarks and antiquarks, gives the neutral baryon. And if we consider the baryon operators with the NC times of the matter field, because we consider NC color gauge group, so unlike the QQQ for the SU3 standard model, for the NC SQCD, the baryon operators consisted by the NC times of the matter field, and it carries the charges of the NC numbers of the baryon. And finally, we can impose the U1R symmetry or R parity. This R symmetry gives the specific supercharges, and for the superpotential case, the R charges of the superpotential W is given by the 2. Because the supercharges or the Rosman variable status carries these R charges. So if we consider the actions with the integration of the displacement variable, then this gives the R charges for the superpotential. Then the gauge now build has a fixed charges of the R equal to 1 because there is a particle. But the matter fields and its antimatter fields carries a non-trivial R charges, which is determined anomaly constraint. So already I said the Q or Q tildes cannot be the Lagrangian term. This is the not gauge invariant. So the gauge invariant operators are given by is the meson, baryon, and anti-baryon field. So that this meson and the baryon operators will describe the physical degree of freedom at the low energy. So this is the similar story for the chiral perturbation theory in the low energy from the QCD in the high energy theory for the non-supersymmetric standard model version, and this is just analog for the supersymmetric theory. But the different point is the dynamics and the Lagrangian are strongly constrained by the holomorphic condition and the other symmetries like as the gauge invariance rule, the global symmetries we impose. So that this uniquely determine the non-perturbative superpotentials at the tree level or only the one level. For example, the ADS superpotential. The ADS superpotential is one example of the SQCD if we consider the SUNC gauge group and the number of the fiber NF is smaller than the number of the color NC. There's a no three levels superpotentials, but the non-perturbative dynamics generalize the exact superpotentials without the loop effect. For the NF is smaller than the NC, baryon cannot be formed as independent moduli, so the relevant operators are given by the meson for this inequalities condition. So the superpotential becomes a function of the meson operators and some specific dynamical scale lambda, which is the highness scale of the SQCD is broken. So now we consider the other symmetry like as the global and the U1R symmetry. First of all, let's focus on the fiber symmetry with the left-handed and right-handed one. Then the mesons are transformed with the left-handed and the right-handed transformation. And the superpotential must be the fiber singlet imbalance under this fiber symmetry. And only the invariant quantity is the determinant of this meson operator because the determinant of the UR transformation and the UR transformation is gives the 1. So the superpotential depends on the meson operators only those is the determinant. And next, we should consider the U1R symmetry. The superpotential terms and actions are given by the discrete setters integrations for the superpotentials, and the Grossman variables carry the R charges of the 1. So the integrations the differential form, the discrete setters carries the -2 of the R charges. So the R invariance of the actions requires that the superpotential has the R charges of the 2. And also we want to make the anomaly free theory for the U1R symmetry with respect to the SUNC gauge theory. So the anomaly cancellation condition for the global symmetry and the gauge symmetry impose the following relation. And only the fermions contributes to this anomaly. So for example, the gauge with horizontal representation, the R charges of the gauge nodes are given by the 1. So this contribution is the 1 times the some fundamentals group theorist quantity. So this gives an NC. And for the matters fermions from the chiral superfields Q and Q tilde, this gives also the contributions of the R charges. And also for the second term. So if we consider all the anomaly condition, summing over the all parameter contribution from the gauge and the matter field, the anomaly cancellation conditions reduces to the following form as a function of the number of the color, the number of the flavor, and the r charges of the matter field, small r. So by solving this equation, we can obtain the r charges of the matter field as a function of the number of the color NC and the number of the flavor NF. So for the r charges of the Mason operator, this is just given by the 2 times the small r, and for example, the determinants of m is r charges given by the multiplication with the number of the flavor. And for the case of the dynamical scale, this has a neutral for the r symmetry. So the r charges are carried only by the determinants of the Mason operator. So we'll use this box r charges of each term when it constructs the superpotential. And for the mass dimension case, the superpotential is the mass dimension of the 3 by considering the action and the integrations of the superpotential over the Gratman variable. And the Mason operator carries the mass dimension of the 2 and the dynamical scale for the mass dimension of the 1. So by considering all of this mass dimension and r charges on the flavor symmetry, superpotentials only determined depends on the determinants of the Mason, and the general forms are given like that, and we can determine the inductor A and the B by considering the correct mass dimension and r charges. And ideal superpotential is uniquely determined by the following form. So the index is given by the functions of the NC and NF, which is the number of the color and the number of the flavors respectively. So by using this form, we can analyze many things for this uniquely determined ideal potentials for the specific inequality condition. The superpotentials are proportional to the determinants of the Mason series, the specific index. And the supersymmetric vacuums satisfies the balances of term by differentiating the superpotentials about the Mason operator. But for the right hand side, with the finite Mason operator, the determinant cannot be the 0, and also the inverse of the Mason cannot be the 0. So the F term cannot balance in every situation. So to satisfy the balancing F term, determinants of the Mason operator should be the infinity. So there was a neo-supersymmetric vacuum for this ADS superpotential, and this is called run-on-away vacuum. Because the vacuums appears for the infinite field value. To stabilize the runaway vacuum, we should ask the three-level mass term. This is a similar story to the non-supersymmetric theory. From the QCD to the chiral perturbation theory, usually we assume that there is a small Clark mass term, and this will give the Mason mass. And similarly for the SQCD, especially the ADS superpotential, we add the three-level mass term of the matter field, and is the conjugate. For simplicity, we take the identity mass matrix, and this can stabilize the vacuum. Upterm conditions are now given by the additional terms from the mass term. So the left-hand side decreases for the large m, the right-hand side is constant, so there is the binary solution which gives the balancing F term. So the mass deformations removes the runaway vacuums and produce the binary supersymmetric vacuum. Also, we can consider the other case rather than the inequality. If we consider SQCD with the same number of the flavors and the color, then the dynamic is the quantitative difference from the previous one. In this case, the Mason determinants given by the following form. This is just a linear algebra, and by the rearranging each antisymmetric symbol and the Cork and the anti-Cork build, the determinants of the Mason operators are just given by the multiplications of the baryon and the antibaryon. So this gives the very strong conditions between the mesons and the baryon operator. Now the meson and the baryon operators are not independent, and this defines some specific parameter space, which is called the moduli space of the vector. This classical constraint can be modified as a quantum impact. The right-hand side must respect all symmetries and the dimension. So for the NF is equal to the NC, all charges of the cork becomes a zero because we bounce this relation. So when the NC and NF is the same, the all charges of the matter fields are just zero. So the all charges of the meson and the baryon operators are also zero. So if we consider this condition, the right hand side has the all charges of the zero. And also these conditions can be written through with the following form. But this gives some specific situations for the origin, which is the meson and the baryon states balances. So there is a new superpotential for the NF equal to the NC state. I will cover this again in the next time because there are additional states. Because we only consider these two reasons, but there are more reasons between the NF and NC. Maybe I will cover this the next time. So we discussed about how the holomorphies and the global symmetry determine the exact dynamics of the SQCD, especially the NF is smaller than NC and NF is equal to the NC case. For the NF is smaller than NC case, the non-perturbative lattice superpotential is uniquely determined by considering the global symmetry, R symmetry, and the holomorphic condition. And they show that the linear vacuums through with the new stable state at the finite field value. So we add the mass term to stabilize this vacuum. And for the special case of the NF equal to the NC, there are the no superpotential generated by considering the UNR symmetries again. But instead, the quantum epochs modified this classical constraint. So okay, so this one, so this comes from the quantum epoch, but the moduli of the space of the vectors so exists, but the geometry of the difference and the origins are removed, so there's some strange behaviors that appears through this case. So these results demonstrates the supersymmetric gauge theory SQCD is allowed exact controls by the strongly coupled dynamics SQCD case by the symmetries and holomorphies condition, and this was extended to the more general ranges between the number of the fibers and the number of the colors and the next time.